Keep the introduction very short. It's a pleasure to welcome Igor Rapinchuk. Igor Rapinchuk is currently an assistant professor of mathematics at Michigan State University. He received his PhD in 2013 at Yale University under the supervision of Margulis. Igor's research interests span several directions in algebra, the theory of algebraic groups, and arithmetic geometry, including structural properties of division algebras, as well as rigidity questions for non-arithmetic groups. In the study of rigidity, he introduced novel techniques that allowed him to resolve new cases of a long-standing conjecture of Borel and Tits, and also to obtain several applications for character varieties. The main focus of his current work is on finiteness properties of algebraic groups over higher dimensional fields. It is the subject of his talk today. Precise title is Algebraic Groups in Good Reduction. Over to Igor.
Okay, well, thank you very much for the introduction, and a big thank you to the organizers for the opportunity to speak in this conference. It's really a big honor and pleasure to be speaking here today. Okay, so let me get started. Okay, so right, so as my the title suggests, the topic of my talk today will be algebraic groups with good reduction. Now, for a little bit of context, so one of the main directions of my work over the past few years has been trying to develop various aspects of the arithmetic theory of algebraic groups over so-called higher dimensional fields. That is to say, function fields of algebraic varieties over various classes of base fields. And recently, a property that has come to the forefront as a kind of a unifying theme has been good reduction. Okay, so to get started, perhaps I should say precisely what I mean by good reduction in this context. Okay, so suppose we have a field K equipped with a discrete valuation V. And suppose we're given a reductive algebraic group G defined over K. Then we say that G has good reduction at the discrete valuation V if there exists a reductive group scheme script G over the valuation ring of the completion, whose generic fiber is isomorphic to the base change of G up to the completion. And then an automatic consequence of this definition is that the special fiber, or the reduction, is a reductive algebraic group over the residue field of the same type as the initial group G. So basically what this definition is saying is that the condition of having good reduction basically means that our group has a nice integral structure over the valuation ring that behaves well under reduction by the maximal ideal. Okay, so this is of course a somewhat abstract definition, but fortunately it turns out that in quite a number of situations of interest, it's possible to describe the condition of good reduction in fairly down-to-earth terms. Okay, so let me mention a few examples of that. Okay, so first of all, one thing to note is that if G is a split group, then G has good reduction at any discrete valuation V. And the reason for that is that by the well-known Chevalier construction, any split group actually arises from a group scheme over Z. So it has good reduction. We can reduce it modulo basically anything we want. Here's another interesting example. Suppose we take a central simple algebra A over K, and we consider the associated group SL1A. So that's the algebraic group corresponding to the elements of reduced norm 1 in A. Then it turns out that this group G has good reduction at V, if and only if our algebra is unramified at V. That is to say, it arises from an Azamaya algebra over the valuation ring. Okay, so that's one nice situation. Here's another nice situation where, again, good reduction can be described fairly concretely. So suppose that G is the spinor group of a non-degenerate quadratic form Q in n variables. Then one can show that this group has good reduction at V, if and only if, up to scalars, our quadratic form is equivalent to a quadratic form all of whose coefficients are units in the valuation. Okay, so this is just to give you somewhat of a flavor of what this condition of good reduction means. Now, before continuing, let me recall one more definition which will be relevant for us shortly, and that is the notion of a K-form of an algebraic group. So again, we fix our algebraic group G over K, and then we say that a group G prime defined over K is a K-form of G if the two groups become isomorphic over a separable closure of K. Okay, so again, let me just mention a quick example. So if A is a central simple algebra of degree n over our field K, then it's well known that over the separable closure, our algebra becomes just a matrix algebra. And therefore, the group SL1A, which we already encountered on the previous slide, is a K-form of the group SL. Okay, so now that I have briefly recalled the notion of good reduction, as well as what we mean by a K-form, let me now formulate the general problem that's at the focus, that's the current focus of our work. Okay, so suppose we have a field K, which is equipped with a set V of discrete valuations, and we take a reductive algebraic group G defined over K. Then what we would like to understand are the K-forms of G that have good reduction at all places V in V. Okay, so this is of course a very general problem, and it's obviously totally hopeless to try to solve it at this level of generality. So to make the question meaningful, one really needs to specialize the field K, the set V, and possibly also the group G. Okay. So that's the general problem. Any questions so far? Okay.
Go ahead.
Okay, so one case that has been analyzed pretty extensively in the literature before is what I like to call the Dedekind case. So here we take K to be the fraction field of a Dedekind ring R, and the set V consists of the discrete valuations associated with the maximal ideal of R. And well, one of the first instances of this that occurs in the literature is work by Harder from the 1960s. And also Kolyetylin and Sansu considered this sort of situation in the 1970s. Now, the basic case where the ring R is just the ring of integers was analyzed extensively by de Grosse in the 1990s. And there is also more recent follow-up work on this topic by Brian Kahn. Okay, so that's sort of the arithmetic situation. Now, another very interesting example, which fits into this general Dedekind framework, and which is of a more geometric flavor, really goes back to a famous result of Raghunathan and Ramanathan. So more precisely here, we take R to be the ring of polynomials in one variable over a field level K. So then capital K is, of course, just a field of rational functions in one variable. And we take V to be the set of discrete valuations associated with a monic irreducible polynomial. And so as far as good reduction goes, here's what this result of Raghunathan and Ramanathan implies. So for simplicity, let's assume that K is a field of characteristic 0, and that G0 is a connected reductive algebraic group over little k. Okay, so then, of course, we can consider the base change of G0 up to the field of rational functions. And now suppose that G prime is a K-form of this base change, which has good reduction at all places V and V. Then it turns out that G prime really just arises as a base change of a K-form of G0 of the base field little k. Okay, so in other words, we get a very nice description of forms with good reduction in this situation. Now, I should say that the original theorem of Raghunathan and Ramanathan was actually stated in terms of torsors over the affine line, but it's actually fairly straightforward to deduce this, this statement from the original result. Now, more recently, Chernosov, Gilles, and Pianzola considered a similar problem over what they call the punctured affine line. So algebraically, they work over the ring of Laurent polynomials. And so I believe that this will be the subject of Volodya's talk, which is next on the schedule. So I won't really say anything more about that. Okay, so what I'd like to just, the point that I'd like to make is that the Dedekind situation is really quite well understood for the purposes of this problem. By contrast, until a few years ago, not much was really known about the higher dimensional situation. And so our work really takes some of the first steps in this interesting and quickly developing direction. Okay, so what is our setup? Well, we take K to be a finely generated field. And then we consider models of our field K, which is to say we look at normal integral affine schemes over Z or Fp, whose function field is this field K. And then to any such model, we can consider the associated divisorial set of discrete valuations. That is to say, the set of discrete valuations of K associated with the prime divisors on our model. Okay, so that's sort of the geometric description of our setup, and really this is the point of view which is most useful in the majority of situations. But if you prefer, one can describe the setup in purely algebraic terms as well. So namely, we take our field K, and inside we consider a subring R, whose fraction field is K, with the condition that R is a finely generated algebra over Z or Fp, and R is integrally closed in K. And then the set V simply corresponds to the height 1 prime ideals of R. Okay, so that's what I mean by the higher dimensional situation. And now, what is sort of the main conjecture that, that our recent results suggest? Okay, so we take K, again, to be a finely generated field, equipped with a divisorial set of places. And we take G to be a reductive group over K. Then our main conjecture is that if the characteristic of our field is good, in a sense that I'll specify in just a second, then we expect that the set of isomorphism classes of K-forms, G prime of G, which have good reduction at all V and V, is finite. And what do I mean by good characteristic? Well, so if G is an absolutely almost simple group, we say that the characteristic is good if it's either 0 or if it does not divide the order of the Weyl group. And for tori, we just take characteristic 0 to be good. Okay, so our main conjecture predicts the finiteness of basically forms having good reduction at all places V in our divisorial set. Okay. So just to mention in passing, I should point out that sort of philosophically, this conjecture has some similarities to the famous Chafarich conjecture for abelian varieties with good reduction that was proved by Faltings. But of course, this similarity is really of a rather superficial nature. I mean, the techniques used in studying this conjecture are really quite different from what's used in the study of abelian varieties. Now, why do we refer to this as our main conjecture? Okay. Well, the point is that, as I already hinted at the start of my talk, good reduction serves as a kind of unifying theme. And more precisely, what this main conjecture does is it brings together several strands in the quickly developing arithmetic theory of algebraic groups over higher dimensional fields. Okay, so let me just quickly mention some of these connections. So it turns out that the main conjecture has some pretty striking applications to the study of local global principles for algebraic groups. and I'll say a little more about this in the next subsection, is also closely related to some natural and actually extremely difficult problems concerning fineness properties of unramified cohomology. Next, it comes up quite naturally in the analysis of algebraic groups having the same maximal tori, or in other words, what is now sometimes referred to as the genus problem. And another very striking application is that the main conjecture is closely connected to the analysis of weakly commensurables risky dense subgroups and applications to some classical problems on locally symmetric spaces. And the reason why this last application is really rather striking is that basically this is one of the first cases where techniques of number theory and arithmetic geometry are being used to solve some long-standing problems in differential geometry. Okay, so that's just to give you an idea of all the relations of the main conjecture to various other problems of interest. Now, in the interest of time, I will focus only on the connection with local global principles. Okay, so let me say a little bit about that now. Okay, so first let me just briefly recall the general setup and the cohomological approach to local global principles, and then I will say more about how our conjecture fits into this picture. Okay, so the general setup is like this. We take a field K, which is equipped with a set of valuations, which are often discrete but don't have to be. And we take G to be an algebraic group over K. So then one can consider the global to local map in Galois cohomology. And then one says that the Hasse principle holds if this map is injective. And another useful object that one encounters in this field is the Tate-Shafarevich set, which by definition is the kernel of this global to local map. Now, the situation which was studied classically was when our field is a number field, and V is the set of all places of K. And then one of the pinnacles of the classical arithmetic theory of algebraic groups is that the Hasse principle holds if G is a simply connected or adjoint. On the other hand, it is known that for arbitrary algebraic groups, the map may fail to be injective, but nevertheless, it is known that this map is always proper. That is to say, the preimage of a finite set is always finite. So in particular, the Tate-Shafarevich set is finite in this situation. Now, what our recent results suggest is that this properness property should hold in the vastly more general setting of finitely generated fields. Okay, so more precisely, suppose that K is a finitely generated field equipped with a divisorial set of places K, of K. So then what we predict is that if G is a reductive algebraic group over K, then the global to local map is always proper. In particular, this would imply that the Tate-Shafarevich set is finite. Okay, so in the next subsection, I will mention some results that we've obtained on both the main conjecture and this properness conjecture. But to conclude this subsection, let me mention the promised connection between local global principles, specifically this properness conjecture and our main conjecture. And the connection looks like this. So suppose that the main conjecture holds for an absolutely almost simply connected group G over K and all divisorial sets of places K. So let me just recall very briefly that the main conjecture predicts that we have basically finite and unity forms that have good reduction at our set B. Okay, so assuming that the main conjecture holds for the simply connected group, then it turns out that the global to local map is proper for the corresponding adjoint group and any divisorial set. So in other words, the point is that the main conjecture provides a uniform approach to our properness conjecture for adjoint. So that's one of the connections of the main conjecture. And now to finish up, let me briefly mention several results that we've obtained on both the main conjecture and the properness conjecture. And I will start with the case of algebraic tori due to the fact that we've managed to resolve both conjectures for this class of algebraic groups. Okay, so what is the precise statement concerning the main conjecture? Well, suppose that K is a finely generated field of characteristic 0, and V is a divisorial set of places of K. Then what we show is that for any integer d greater than or equal to 1, the set of K isomorphism class of d-dimensional K tori, which have good reduction at all V and V, is finite. Okay, so that establishes the main conjecture in the setting. Now, notice that here I assume that the characteristic of our field is 0. Well, we actually also have a similar statement in positive characteristic, provided that we restrict ourselves only to those tori which split over an extension of degree prime to P, where P is the characteristic of the field. So there again, for such tori, we have a fineness statement for d-dimensional tori having good reduction in all places B. Okay, so that takes care of the main conjecture. What about the properness conjecture? Well, here we actually work in a somewhat more general setting. Namely, we consider not just algebraic tori, but possibly disconnected algebraic groups whose connected component is a torus. So the precise result looks like this. Suppose that K is a finely generated field and V is a divisorial set of places. And let me just emphasize that here we do not impose any restrictions on the characteristic of our field. Then what we show is that for any algebraic group D over K, whose connected component is a torus, the global to local map is proper. So in particular, this implies that if we take our group to be a torus, then the Tate-Shafarevich group is finite. Now, one of the classical facts of, well, basically class field theory is that the Tate-Shafarevich group for a torus over a number field is finite. And this proof relies on Tate-Nakayama duality and various other considerations of class field theory, which are not available in the general setting of finely generated fields. Okay, so to prove our result, we actually have two approaches. For tori, one can argue using absolute purity as proved by Garber, but here one needs to impose some minor restrictions on the characteristic of our field. And to handle the general case, so specifically the case where our group is not necessarily just a torus, but a group whose connected component is a torus, we develop some adelic models. And the interesting thing is that the second approach shows that the finiteness of Tate-Shafarevich group for tori over number fields can be deduced from two classical results in algebraic number theory, namely the finiteness of the class number and the finite generation of the group of units. Okay, so I should say that the approach using class field theory, of course, gives more information. Actually, it describes the structure of the Tate-Shafarevich group. But if one is interested in establishing only the finiteness, then the full strength of class field theory is not. Okay, so that takes care of algebraic tori. And now just to finish up, let me quickly mention some results for semi-simple groups. And I should say that by contrast with the case of algebraic tori, here there are still quite a few open problems. But in any case, we've managed to resolve the main conjecture in a number of cases. So for instance, for inner forms of type n over arbitrary finely generated fields, then for spinor groups over so-called two-dimensional global fields, that is to say function fields of curves over number fields and surfaces over finite fields, as well as function fields of rational surfaces. Also several cases for groups of type G2. And for the properness conjecture, we get the properness of the global to local map for PSL1A over arbitrary finite generated fields, quite a number of cases over two-dimensional global fields, and also several cases for groups of type G2. Okay. But as I said, whereas our understanding is pretty much complete in the case of algebraic tori, here there remains quite a lot of work to do, although there is already quite considerable progress. Okay, so my overview of the results was a little fast, but I should say that if you're interested in looking at these questions in a little more detail and seeing what has been done and various open problems, I can suggest our recent article in the notices of the AMS, and also our more extended survey on this topic, which is item 7 on this list of references. Okay, so I think I will stop here.
Thank you, Igor. Thank you. So questions, please. Anybody has questions, you could ask. Unmute yourself and ask.
Okay, I have the books here.
Yeah.
You mentioned applications to cohomological finiteness properties in the unramified case, and I see it's reference number 4. So could you say a little bit about what that was hinting at?
Yeah, so the application, so for instance, let me go back to this slide. So I say we resolve the main conjecture for spinor groups over two-dimensional global fields. So remember, this is saying that we have finitely many forms with good reduction. And the point is that using Milner's conjecture and quadratic forms, we basically reduce this, this statement to a certain finiteness statement for unramified cohomology. That is to say, we need unramified Galois cohomology with respect to our set of discrete valuations to be finite in all degrees. So that's the connection that I was hinting at.
Thank you.
Mm-hmm.
So,
Some other questions? I had a small question with, can you say something about applications to the genus problem you mentioned?
Yeah, so the application to the genus problem basically, it relies on the following statement, which is basically, we consider our group G, and we assume that our group has good reduction at a place V. Then under some hypotheses, we show that any group in the genus of G, that is to say, any group which has the same maximal tori, also has good reduction at V. And then using our main conjecture, so assuming that we have only finitely many forms with good reduction, this would imply the finiteness of the genus.
Thank you. Are there any other questions? Okay, if there are no more questions, let's thank Igor, and we'll have another 10 minutes for the next